An automotive radar system is a technology used in vehicles to detect and track objects in their vicinity. In the automotive context, radar systems are primarily used for advanced driver assistance systems, ADAS, and autonomous driving applications. These systems operate on the principle of radar, radio detection and ranging, which emits radio waves and capture the reflections to determine the range, speed, and direction of objects. Automotive radars are used in adaptive cruise control, ACC, automatic emergency braking, blind spot monitoring, rear cross-traffic alert and collision warning systems. FMCW, frequency modulated continuous wave radar, also known as continuous wave radar with frequency modulation, is a type of radar system used in various applications. Unlike traditional pulsed radar, which sends short bursts of radio waves known as chirps and then listens for echoes, FMCW radar emits a continuous waveform with varying frequency. The transmitter alters the frequency of the transmitted signal in a linear or ramp-like manner. The frequency change rate is known as the chirp rate. These chirps are transmitted using antennas. The reflected signal is mixed with the transmitted signal still being emitted. The mixing process results in a new signal known as the beat frequency or intermediate frequency. The radar's receiver analyzes the beat frequency. The beat frequency is directly proportional to the range, distance, between the radar system and the reflecting object. By measuring the change in frequency over time, due to the frequency modulation, the radar can determine both the range and relative speed of the target object. In addition to measuring the range, FMCW radar can also use the Doppler effect to detect the relative velocity of the target. The Doppler effect causes a shift in the frequency of the reflected signal based on the object's velocity relative to the radar system. By doing operation we get all the range, speed, angle information of the surrounding objects. Advantages of FMCW radar include continuous and real-time monitoring, high range resolution, and low power consumption. In 77 GHz to 81 GHz frequency, we have limited range. To increase the range, we couple multiple transmitter antennas, creating a radar beam. But this increases the time to scan the scene, reducing the velocity resolution. As a solution to this problem, we proposed a radar system with multibeam beamforming to increase the range without trading velocity resolution and scan time. Our radar system can detect up to 300 meters and an object very small as a cyclist. We designed a system capable of transmitting radar signals and process the reflected signals to calculate radar points on each object. These points will be fed to a machine learning model to detect objects like vehicles, humans in a scene. We have four main parts in our design: an RF PCB, an interface PCB, a radar signal processing unit and an ML classifier. At the end, we get the classified targets. Under the implementation, we created and tested the antennas and the antenna pattern. Then we designed the RF PCB, which is a high-frequency 8-layer design. This has 4 radar transceiver chips and all the components required for the transceivers to function. Our next step was to design an interface PCB which controls the transceiver chips and captured the raw radar data to our processing unit. Next, we designed the radar signal processing unit on an FPGA. This will perform computations on the captured data and output the radar point cloud information. Finally, we send the radar point cloud information to our ML classifier. This is a novel graph neural network-based method. This will first cluster the points, grouping them together, and then classify them as different objects. FMCW automotive radar is an emerging field in autonomous automotive applications. These will soon surpass existing camera and LiDAR sensors. Radar systems are less affected by light conditions unlike cameras, has velocity measurement capability with longer ranges.